Hopefully this presentation will help you understand acceleration a little better. I'd like to start with two video clips. Acceleration tells us, or is a measurement of how fast velocity changes, but what does that really mean? Take a look and let's find out. In this clip, you see a roller coaster. Hopefully you've had a chance to experience roller coasters before. You know that they go up, they go down, they go side to side, they go loop to loop, and all of that represents acceleration. Acceleration happens when the coaster goes down because it's speeding up. Acceleration happens when the coaster goes up because it's slowing down. When this coaster comes to a stop and reverses direction, you are experiencing acceleration. You feel that acceleration in different ways as you're riding the roller coaster. You might feel it as a side-to-side motion. You might feel it as getting thrown forward in your seat. You might feel it as getting pushed back in your seat. So let's take a look at how that might affect the way you feel acceleration.
There appears to be some confusion about the difference between accelerating and moving at a constant velocity.
Yes, this is a very hard thing to understand.
It comes down to balanced or unbalanced forces.
Or if your stomach can feel it or not.
If the forces are unbalanced, your stomach can feel the acceleration.
Like if you were on a roller coaster or the Gravitron ride.
Or in a car when someone hits the gas or the brakes very hard.
Or in the back of a bus when it goes over a dip or small hill.
I love that, but all those things can make me sick.
Yes, acceleration is fun but can make you sick too. That is why they have a trash can with a plastic liner at the end of some rides at Hershey Park.
Ah, what you are saying is that acceleration makes people blow chunks.
That could be the fourth law of motion. Acceleration makes you throw up.
But moving at a constant velocity does not. Constant velocity and stationary are actually the same thing. When you move at a constant velocity, your stomach feels nothing, and you do not lose your lunch.
That would be when you are in a car going at a constant 60 miles per hour. Or on the earth spinning at a constant 1,000 miles per hour.
Or on the kiddie rides at Hershey Park. They do not have a can with a plastic liner.
Let us get back to the car going 60 miles per hour. You were saying that the force of the engine is totally cancelled out by air resistance? And this results in balanced forces?
Yes, if the engine pushes at 100 newtons and air friction is 100 newtons, the forces are balanced, and you are not accelerating.
Or blowing chunks.
Or blowing chunks.
One last way to think about it is if you can get up and walk around or not.
If you can walk around, such as on a flying airplane, you are going at a constant velocity. If you cannot, you are accelerating.
That is why you should not stand up on a roller coaster or in a bus when the driver slams on the brakes.
To review, constant velocity does not make you sick, acceleration does.
It is easiest for me to remember that acceleration causes an object to blow chunks.
So, find Study Guide 1.3 and let's take a look at some of those answers that you filled in yesterday. First, we need to preview the section. Look at the following to see what you're already familiar with. Look at the Now You Will Learn objectives. Reread all the headings and subheadings. Check out the pictures and the captions that go with them. And make sure you understand the vocabulary terms. I'll give you a moment to do this. Great. Now let's focus on the review, which is found in the Before You Learn section. The review question says, if Sam is walking north at a rate of 5 meters per second, did he describe his speed or his velocity? Check out what you wrote down. If you said he was describing his velocity because he includes his direction, you are correct. Make sure you have the correct answers for your study guide. All the answers in the PowerPoint that you need will be green. Our first heading says speed and direction can change with time. Acceleration in the real world usually means something is speeding up. However, acceleration in the science world means the rate at which velocity changes. But this can be an increase in speed, a decrease in speed, sometimes known as deceleration, and a change in direction. So acceleration in the science world really means 3 different things. Here are some examples of increasing speed. For example, a car speeds up at a green light. It starts out at a stop, and then its speed gets faster and faster as it goes away from the green light. Decreasing speed might look like a car slowing down at a stoplight. The car is going fast, but then as it gets toward the stoplight, its speed goes less and less. And finally, a car taking a turn, which can be at a constant speed, is also a type of acceleration. Speed and direction can change with time. Acceleration measures how quickly speed and direction are changing. Notice these are green, which means they belong somewhere on your study guide. What does that actually mean? If the speed of an object increases, or the speed of an object will increase when acceleration is in the same direction as motion. Think about if you're pushing a shopping cart and a friend comes up behind you and pushes on your back. Your speed is going to increase because of that increased force that's going in the same direction as you. The speed of an object will decrease when acceleration is in the opposite direction as motion. Again, think of that same shopping cart. If your friend now comes up to the front of the shopping cart and pushes against your motion, you and the cart are going to slow down. Finally, the direction of an object changes when acceleration is at an angle to motion. So if your friend comes up to the side of the shopping cart and pushes on it, it's going to make the shopping cart and you turn. Now let's look at calculating acceleration on page 28. In order to measure acceleration, you must know the change in velocity and the time. The change in velocity actually involves 2 different things. In the equation, it becomes acceleration equals final velocity minus initial velocity divided by time. Remember that initial means the beginning, like the initials in your name indicate the beginning letters of your name. So you start with the final velocity and then you subtract the initial velocity and then you divide your answer by time. The units for acceleration are known as meters per second, or another way to say that is meters per second squared. Think about that for a moment. Think of acceleration like an interval. An interval is the number you count by, like 1s or 2s or 5s or 10s, like when you're doing a graph. If the acceleration of an object is high, like if you were counting by 10s, the object will gain speed very quickly. So for example, if you were talking about a sports car like a Lamborghini, a sports car can start at 0 and reach 60 miles per hour in a very short amount of time because its acceleration is very high. Or like a rocket taking off. If the acceleration is low, like counting by 1s, 1, 2, 3, the object will gain speed very slowly, like trying to ride your bike faster while you're going uphill. You can push on the pedals harder, but it's going to be difficult and it's going to take more time to increase your speed. Take a look at these 3 cars. Which car is accelerating the most? If you said the blue car is accelerating the most, you're right. All 3 cars accelerate, They all change speeds. However, the blue car changes its speed in the fastest amount of time. Now if we add some data to the bottom, you can see how this really happened. Let's look at the data for the blue car and calculate its acceleration. We see here that at 0 seconds, the blue car's acceleration is 0 meters per second. By the time it gets up to 4 seconds, the blue car has sped up to 16 meters per second. So if we plug this into our formula, it would be final velocity, 16 meters per second, minus initial velocity, 0 meters per second, divided by the total amount of time, which is 4 seconds. This means 16 minus 0 is 16 meters per second, divided by 4 seconds gives us an acceleration of 4 meters per second squared. That means this car's speed is increasing 4 meters per second every second. So it goes 4, 8, 12, 16. Here are a couple questions to think about. How can a car be accelerating if its speed is a constant 65 kilometers per hour? It's accelerating if the car is turning. Here's another one. If an object has slowed down, how does its final velocity compare with its starting velocity? Think about that blue car for a moment. Imagine that instead of speeding up, it was slowing down. If it's slowing down, that means its final velocity would be less than its initial velocity. And if you think through the equation, that means you would end up with a negative number as your answer. Here's another one. If you accelerate at 2 meters per second squared, how much would your velocity increase every second? Remember to think of acceleration like an interval. So in this case, 2 meters per second squared means you're counting by 2's. So your velocity would go up by 2 meters per second every second. How long would it take you to reach a velocity of 6 meters per second? If you're going up by 2's, it would take you 3 seconds. 2, 4, 6. That would be 3 seconds to reach 6 meters per second. When you graph acceleration, there are two different kinds of graphs you can use. You can use a velocity versus time graph, which we've already looked at. We called it speed versus time. Velocity versus time, which we have not looked at, and distance versus time, which we have looked at when we were graphing speed. Take a look at the graphs on page 30 in your blue textbook. Here's an example of a speed versus time graph. Imagine this is a graph for this guy riding his bike down a hill. You can see the speed on the y-axis goes up to 14 meters per second, and the time on the x-axis goes up to 6 seconds. If you look at the line, you can see that every second his speed is increasing. This is an easy way to understand acceleration. At 1 second, he's going 2 meters per second. At 4 seconds, he's going 8 meters per second. And at 6 seconds, he's going 12 meters per second. His speed is increasing with time, which means he's accelerating. On this kind of graph, a straight line means acceleration. It also means that the acceleration is constant, meaning it's the same amount of acceleration each time. Now, if we take a look at acceleration on a distance versus time graph, you see that the line has changed. It's the same guy riding down the hill on his bike. But in this case, we're looking at distance versus time. So for every second that passes, we're looking at the slope of the line now. You can see that the slope of the line starts to get steeper every time 1 second passes. We learned before that distance versus time, the steeper the slope, the faster the speed. So this produces a curved line, which means the object is accelerating. The curved line also means that your speed is increasing. Now take a look at this graph where I have 4 different lines for you. Which line or lines represent an object that is accelerating? Notice that this is a distance versus time graph. If you said the black and the red lines represent objects that are accelerating, you were right. Let's look at the black line first. Right here, the black and the green are at the same points, but when you get to 3 seconds, the black starts to go uphill in a curved direction. That means the slope of the line gets steeper for every second that passes. So in this case, the black line is representing an object where its speed is increasing. The red line is also accelerating. In this case, though, we start out high and the slope gets less and less. So that object's speed is decreasing. It's getting slower. The green and the blue lines are straight lines, which means they have a constant speed. Now I have 2 video clips for you to watch on IME. They are under class assignments and then acceleration video clips. What I'd like you to do is take notes on those 2 video clips. They review everything we've talked about so far: speed, position, time, and acceleration. Make sure you put your notes on a separate sheet of paper and make sure you have your name on it.